thank you very much for organizing this event. I'm very happy to be presenting this project, which is about the impact of climate change on maritime transportation and trade through the impact that climate-induced weather shocks can have on ports. So the motivation comes from what we can hear in the news sometimes about ports being closed or disrupted by weather events. So for instance, in the US, last October, when Hurricane Milton hit Florida, all ports of Florida had to close. And these are not only anecdotal and very localized events, because it's disrupting maritime transportation, which is essential for international trade, as about 80% of internationally traded goods are seaborne. And when you have this kind of weather events impacting maritime transportation, impacting the port, it translates into a non-operability day for the port, where it cannot unload and reload ships, at least partially. And so this creates, so not only it blocks the port, but it also creates some congestion as it reduces the port capacity. And congestion is really increasing shipping costs because the ships, they need to spend longer in the ports, which is very costly. And in addition, shipping really works in a network fashion where all ports are interconnected. So what happens in one port can actually very easily spill over to other ports. So if you think, for instance, what happened in 2021 when the Suez Canal was blocked because there was a ship in the middle, so it was not a port, but it was a very localized event, and it created a massive disruption of the whole maritime transportation. So from one localized event, you can potentially have global consequences. And finally, those weather events that are impacting ports, they're expected to become more frequent and worse with climate change. This is what the IPCC shows, especially because of sea level rise and associated weather events with storm surge, coastal flooding, and stuff like that. Ports will be more and more frequently disrupted. So that's why the objective of the project is to study the global impacts that climate change can have on ports in the context of the shipping network that allows port spillover effects. So the work that I do is that I first estimate how weather shocks can affect port efficiency and hence affect transportation costs using some detailed shipping data that I will present. And I then try to include these effects in a general equilibrium model of international trade with transportation, especially with a shipping network that includes port congestion that will amplify the effects of weather shocks. And with this model, I can estimate counterfactuals using projections of how sea weather will evolve with climate change. So some climate scientists have been showing that ports will be impacted in the future and very heterogeneously. Like some ports will be kind of protected because of where they are situated and because of their special infrastructures, whereas some ports will be completely underwater. But what I show with my model is that even ports that are fairly protected are actually going to be impacted by the spillovers coming from other ports that are themselves very exposed. So I can quantify global effects on maritime traffic, on trade, and as well as a heterogeneous distribution.
Just ask a clarifying question.
Yeah, sure.
So you talked about disruption at the port and then disruption at another port that influences congestion in the network.
Yeah.
Are you going to capture anything or speak to how these shocks are also influencing what's going on in between, if it's causing delays and reroutes and that sort of thing? Or this is about exposure at the port level?
So it's about exposure at the port level that then can cause reroute and stuff like that. So I'm not going to talk, I can talk now about shocks happening in between ports, like in the routes. Yeah. It happened that for shipping is not so much a problem because when you have, for instance, bad weather along the route, it's very easy for ships just to go around it. So it will create some delay, but easy to go around it, whereas in the port, you cannot just change the location of the port. And what's specific also about the ports is that it creates congestion. And it can impact ships arriving after the bad events because ships were blocked before. Whereas at sea, you don't have congestion because you can just go everywhere. So actually, I don't have it here, but I have evidence that weather along the route has a much smaller effect than weather on the ports. So that's why I focus on big routes. And so it's building on literature that's looking at trade, including a transportation network. So this literature, so I rely a lot on Allen and Arkolakis, for instance. This literature is usually more focused about transportation happening on land, like highways, or railroads. And there is a strand of literature now with Helen Ganapathy, Brancaccio, that's going more to modeling the shipping sector. So I'm trying to go further into modeling the specificities of shipping network as opposed to transportation network on road. Specifically, I will focus on ports and congestion that can happen in ports, as opposed to, for instance, highways where you have more congestion on the links of the network. I also use this kind of AIS data that I will present, used to study more traffic on the link. I focus on the ports. And so I contribute also to the environmental literature, trying to quantify the impacts of weather and climate change on economic outcomes. So I try to focus on the impact it can have on transportation, and especially on maritime transportation, which can be related to weather shocks both at sea and on land. That's it. So I'll be presenting the data and some readers from evidence to hopefully convince you that this is something we should matter about. Then I will present briefly the model I'm using, estimation of key structural parameters, and some first counterfactual results. So the data is based on this technology that ships have a transponder. They need to send their exact position at every point in time. So it's called automatic identification system technology. And so from this, I can build a data set of port calls. That is to say, every time, so I'm focusing on container ships, and every time a container ship enters or leaves a port, I get the exact position and the exact time. So I got it for the whole universe of container ships in about 1,700 ports from 2015 to 2023. And from this, I can build measures of how efficient ports are. So based on the literature, so a fast measure is a dwell time. It's how long ships spend in the ports to be serviced, so to be unloaded and then reloaded. So it measures port efficiency because ships, ideally, they want to go very quickly because staying in the port is costly. And I can also compute, so this is the dwell time for the biggest 50 ports in my sample. So you see it's between usually 40 and 60 hours for a ship. This is the number of entering calls in the port. So that's to say the number of ships that come in the ports here every week. So that's also a measure of how efficient the port is. And it's between 10 and 12 ships. So a number of calls weighted by the ship capacity, of course. So with this shipping data, I match it with weather data. So port efficiency can be affected by a bunch of weather. What I focus on now is wave heights. So it can also be impacted by wind, by storm surge. I use for now wave heights as a proxy for all the weather that can impact ports, but I plan to include a more extensive set of weather measures. And so from the global analysis ERA5 datasets, I match it with position of the ports so that I get the average daily wave heights for each port each day. So this is the average for the biggest 50 ports. So as you can see, there is pretty much seasonality, but there is also day-to-day variation that I will be exploiting for some measures from evidence. So the first exercise I'm conducting, yes, sir.
Is there like an adaptation mechanism for wave height? Like if I build a seawall or something like this, would that help?
Yes, exactly. So there are possible adaptation mechanisms. So for instance, exactly building seawalls. For instance, the port of Rotterdam has been building seawalls. I can also see in my data some heterogeneity that the ports that are the most exposed, most frequently exposed to very high wave heights have a lower impact of wave height than the ports for which it's very exceptional. So yes, there is definitely some adaptation mechanism, which I've not yet included in the project, and it is something that I would like to do. So I won't address it today. And so I first just regress a measure of port efficiency, so either the dwell time or the number of entering call. So on port I on day T, on just the weather of these ports, including ports and day fixed effects, or any possible fixed effect. I've tried with port month, country day. It's actually fairly robust to any kind of fixed effect I could think about. Each time I find that increasing the wave height, so here this is in measure, it increases the time that the ships spend in the ports, and it decreases the number of ships that are able to actually enter the ports. And actually, this effect is pretty nonlinear. So here instead of having this continuous wave height variable, I just divided it into bins based on the distribution of wave height in each port. And I find that it's really the most extreme events when wave height is very high that drives the results. And also, this event lasts in time. So this is an event study where I just look at the effects of having an extreme wave height, so higher than the 99th percentile. And what I can see is that so it impacts the dwell time, it's rises it, but it also has an effect before and a little after. And same on the number of port calls, it reduces it also on the day before, the day after, and then there is a slight catch up, but not enough. So yeah.
To discretize this, is there also some measure from, I don't know, port authorities, what they define as storm conditions where they wouldn't let ships out or in, maybe as an idea?
So yeah, there are, but I think it depends on the location of the ports. So I don't know, about French ports, for instance, I know, yeah, there are some thresholds, but it's really like, yeah, dependent on the port authority. So here, and I'm considering ports all over the world. I've not used these thresholds, but yeah, I could have some, yeah, like general thresholds. So local weather can have an impact on local port efficiency. What I would like to show also is that a port efficiency can be impacted by the weather happening somewhere else, especially in other ports of the network. So to do so, I build measures of weather downstream and weather upstream of a port. So from a given port, a port downstream is a port where the ships go when they leave the port, and a port upstream is where the ships come from when they go to the port. And so weather downstream is just a way, yes, sorry.
Sorry, can I ask, to what extent is this forecastable if you do heterogeneity effects over time?
Yeah, so this is forecastable. I mean, ships, they have, I mean, especially container ships, they have very good forecasts about how the weather is going to evolve. So especially to determine exactly the trajectory, if they should like especially go around a little when there is bad weather. But in the ports, there is not much they can do. So something they can do, for instance, when they know that there will be bad weather at their destination port, they can slow down a bit on the route. So this I find that there is bad weather in the destination ports. It increases the time to get to the ports. So it means that the results I have are rather lower bounds. Because, yeah, but there is not much I can do. Yeah.
But on that point, how far in advance are they forecastable? I mean, one can imagine if you've got an optimal routing problem and you know a week in advance, the optimal routing problem would give you a different order or something. So obviously if it's, you know, a few hours, then you're en route and they go.
Yeah, so usually it's, I think, a couple of days. But the thing is with container ships, they have routes that are very determined in advance. They really work like buses where they have some stops and they just go around them. So the best they can do is maybe stop stop a port. So, but it kind of depends. If there's like a major port where they're supposed to unload a lot of container, then they're not going to stop it. So they have very little flexibility, actually. Rather, in the long term, they can modify the routes, but not so much adapt in the short run. And so yeah, I build a downstream weather as a weighted average of weather in all downstream ports. And the weights I actually observe in the shipping data, I can see all the ships going from one port to a downstream port, which I divide over all the like ship flows, leaving port I to go to any downstream ports, and same for upstream. And I can then regress efficiency of port I on its own weather, downstream weather, and upstream weather. And what I find is that indeed, so a port's efficiency is affected by its own local wave height, but also by the wave height of downstream ports. So when downstream ports have bad weather, it increases how long ships will spend in my ports and decreases how many ships are going to my ports. So this, a mechanism driving this could be some anticipation. If like I'm a ship in a port and I know that the next port will be locked, well, maybe I stay a bit longer in the port where I am currently. But so this is some evidence of spillovers happening through the network. So that's why I moved to a model to try to understand a bit. Yes, sorry.
Sorry, can I just ask on the last point? So is it cheaper if I'm a ship, is it cheaper for me to stay where I am than to like slow down on my route to the next place?
Not exactly, because as long as you stay in a port, you need to pay some port fees. But maybe, I mean, if you have also, I mean, one advantage also is that when you are in a port, you are fairly protected. Like not much could happen to you in terms of like security. Along the routes, when there is a storm, it's better to be inside a port that's along the routes. So it might also be a reason if there is bad weather, like why ships want to stay in the port, even if it's a bit more costly. Yeah.
But I guess related that for you, what really matters, it is the cost of this disruption in the sense of the overall economy, right? The increasing shipping times, how that eventually will map into price of goods and this sort of things, right? You're not really caring, I guess, on the private cost of the firms that are shipping, right? Or this is going to be part of the equation as well.
Yes, so this is why I use this model to be able to quantify global cost. The thing is, I don't actually observe prices of ports. It's super confidential data. So I'm relying on this, how long the ships spend in the ports to have this elasticity, and then using an elasticity of how costly, the time cost, basically in transportation, to be able to estimate this global cost.
From a sort of consumer point of view, right? In the economy, what's going to be a normative welfare measure, I guess.
Yes, I assume perfect competition, so any increase in cost is just passed through consumer direct. So I use spatial economic model by Allen and Makalakis with endogenous route choice and transportation cost based on congestion that I adapt to shipping and to an international setting. So just to walk you quickly through the key mechanism of the model, I have a finite number of ports. And those ports, they are connected by a transportation network. So this transportation network actually is represented by two matrices. The first matrix is a matrix of links cost. So it's just the cost of going directly from a port I to a port J. So it's an iceberg trade cost. But maybe sometimes you don't have a ship going directly from port I to port J. In this case, the link cost would just be infinite. So this is very common in any model with transportation. It's just the cost of going along a route, for instance. What I add is a cost of matrix of nodes cost. So PI is the cost of just going through port I, because you need to pay port fees, to pay for the ships to be unloaded, reloaded, and so on and so forth. And then goods, they will move from an origin I to a destination J through a route. This route is very unlikely to be direct, as you don't have direct connection between any port. It's most likely to be indirect. That is to say, you will need to go through some intermediate ports. So for instance, if you want to go from I to J, and you decide to go from intermediate port K1, K2, K3, then since it's either port, everything is multiplicated, and so you will pay the cost of starting from port I, then the cost of this leg, the cost of this node, leg, node, and so on and so forth. So you will end up with this multiplicated cost. Yes.
Where's the notion of time? That's not indexed by the amount of time you're spending in it. There's a fixed node cost, or the node cost can vary.
So the node cost, so I will specify that it's a function of time.
Okay.
And then this time will depend on congestion and weather.
I see.
And you actually have many routes possible to go from I to J. So maybe you can go, choose a longer route or whatever. And so the decisions of agents in J will be, they will choose where they want to source their goods from, so from I, and through which routes they actually want to import their goods. So there are these two decisions, such that it looks like a very standard Eaton-Colton trade model, where I get a gravity equation that relates the trade flows between I and J, that depends on an origin term, a destination term, and some transportation costs. It's just that usually this transportation cost is exogenously given. Here, it's going to be a function of all the routes possible to go from I to J, and the costs of all the nodes in between, and all the links in between. And so this is a gravity equation for trade, so that is to say what's produced in I and consumed in J. What I add is a gravity equation about traffic. So traffic along a link, for instance, is all the goods that are flowing through these links. But maybe they come from another origin, they go to another destination, but at some point they will be on this link. And so I can have a gravity equation for all the goods traveling on this link, and also all the goods that are in one port at a given moment. And so all these goods, they will create some congestion because there will be some extra ships in the port. And so what I will show you now is, so indeed, how I specify the cost of ports and nodes. So I assume that the cost of links is exogenously given. So just, I mean, function of distance or whatever, as opposed to usually on the road network where here you can have some congestion and the cost of a highway depends on how many other people are on the highway. But here I will have congestion on the cost of the node. So in a very simple way of interpreting the last word interview about Julia cache encoders, I assume that the cost of staying in a port is a convex function of how much time you spend in this port. And how much time you spend in the port, it depends on how many other ships, I mean, on the traffic in this port, divided by the port capacity, like how efficient the port is at, or just its infrastructure. But the port capacity is also a function of weather, because when you have bad weather, the port needs to shut down, or just, I don't know, the cranes cannot work when there is too much wind, and so on and so forth. And so putting all this together, I get that the cost of a port, so it has an exogenous component. It also depends on weather and on traffic in this port. And so I have two key elasticities. The lambda is the congestion elasticity, so how much cost of a port increases as a function of traffic in this port. And then the weather elasticity, so how much the cost of a port increases when there is bad weather. And so I will use the shipping data to estimate these elasticities. So I'll just combine the equation about time and about weather to have an estimation equation directly derived from the model, where I relate, so the time spent by ship S in port I on day T on the traffic in this port. So I look at the traffic not only on this very day, but also on the days before, as congestion can have long-lasting effects. So I take a moving average over the past 14 days. And also I look at weather along the past 14 days. And I include ship port fixed effects, day fixed effects, and port year fixed effects. And the way I measure traffic is all the ships that are simultaneously in the port weighted by their capacity. One problem with this estimation equation is that traffic is endogenous, because maybe there is reverse causality, and when you see that there is a high dwell time in a port, you decide not to go there, so it reduces traffic. Maybe there are some unobserved components of port efficiency that affect both traffic and dwell time, so I need to instrument for it. The way I do it is using what I found in the reduced form evidence about spillovers. I found that the port efficiency can be affected by weather in other ports. So I instrument traffic in one port with weather in downstream ports, with the same weights that I've been taking from the shipping data. And so what I find that my instrument performs decently, which is cool. And I find two elasticities. So the elasticity of dwell time to traffic. So when I increase traffic, it also increases the time ships spend in the port, which is consistent with congestion. And also, so here I use wave average height. When there is bad weather, it increases dwell time. So those are the two elasticities that I will be using to run counterfactual in the model. So to run counterfactual, I consider in my set of ports the biggest 400 ports in 2019. The data I need to estimate counterfactuals, I need outcome and expenditure at the port level. So I take them at the country level and then allocate them to ports. And I also need traffic data that I observe in my shipping data. The counterfactual I do is I shock weather in each port. So this delta weather, and then I rewrite my model with exact hat algebra techniques so that I can derive changes in traffic along links and on ports, and also in real outcome as a consequence of this change in weather. So what I would like to do ideally is to have these changes in weather according to climate change projections. I've not done it yet. What I will show you is the result. It's kind of a third experiment. I just shock the weather in one port and no other ports. So it is always an experiment because, of course, if one port is affected, well, maybe there is also bad weather in the ports around. The objective is just to show you how the spillovers work and how shocking only one port can affect other ports. So the ports I will be shocking is the port of Singapore. So here, what you see here is the effects on traffic routes. So all the routes that are going to Singapore or coming from Singapore have decreasing traffic. And what's interesting is that all the routes in the region that are not directly connected to Singapore, but around, have actually slightly increasing traffic because of traffic flows diversion. Looking at the traffic on ports, of course, Singapore has decreasing traffic because it's now more expensive. And the ports around also have decreasing traffic because they had a lot of traffic with Singapore, so now it's decreasing. I can also look at the effect on real outcome in port areas. So the numbers, I mean, maybe they don't mean a lot. The objective is really here just to compare, to see what's happening and the sign of the effect. So in Singapore, it's decreasing real outcome because they are hit by bad weather. Actually, in the ports around, it's rather increasing very slightly real outcome because as a consequence of lower traffic, they have lower congestion, and so it ends up reducing slightly their trade costs, which benefits. Another exercise I can show you is, so I take each port, I shock it, and I look at the effects on global outcome. So the color of each port is how much global outcome in the whole world reacts when this port is shocked. So it's kind of a measure of how a port is critical for global welfare. And what I can see is that the ports that have the biggest impacts on global welfare seem to be, for instance, Lagos in Nigeria, ports that are pretty isolated. In regions where there are a lot of ports, for instance, in Europe, it's so dense, and when a port is affected, actually, there are multiple alternative substitution possible. So, and one also interesting thing to see is that some ports have a slightly positive effect on global welfare. So when they are shocked, it actually improves global real outcome. This comes from the externality presented in the model that there is congestion. And so some ports are so congested that actually when there is a shock hitting them, it forces reallocation to other ports, which end up being beneficial. So it's very, very small magnitude, but this is because I'm shocking only one port. With climate change, basically all ports will be shocked at the same time. So yeah, about the next step, I plan to use a more extensive set of measures of sea weather and to use projection to run some kind of actual. Many things I need to work on, linking short-term to long-term, and also I'll try to model a bit more, again, the specificities of the shipping network, especially using its flexibility. Yes?
So I'm just curious, if it's a reallocation effect, if all the ports are shocked at the same time by the same magnitude, is it neutral?
So they're not going to be shocked at the same magnitude because first, the effects of climate change is heterogeneous. For instance, I don't know, in Southeast Asia, it's going to be way more important impact that's, I don't know, in Europe, for instance. And it also depends geographically. It also depends on the exact infrastructure of the ports. For instance, ports that are located inside a harbor, they are pretty much protected, whereas some ports directly into the ocean will be much more impacted. So all ports will be kind of shocked together because climate change is global, but very heterogeneously. So the global impact will be negative, but with lots of heterogeneity.
It was mostly to understand the modeling behind it, right? So currently, do you have two intensity, like the local effect as this, and then you have the reallocation? Yeah. Or is it just a reallocation effect?
So in what I've shown you, I have a local effect because I shocked, but in just one port, like what I've shown you, just a local effect in Singapore. And then I have a distribution of effects in all other places that had not direct effects, only indirect effects. Yes.
Do you also see the ship type? Because maybe it also influence. And so do you see the wind directions, whether it's against the route or?
So I see the wind direction. About the ship type, yes, I only have container ships here. So there is heterogeneity in container ships as like there are some very big ones and some rather small ones. I've done some heterogeneity at the ship level. The size of the ship does not seem to induce lots of heterogeneity. About the wind, yes, it's also an important component. As I'm looking on the effect on the ports, the direction of the wind is not so important, but it's a very important factor as, but it's very correlated to wave height. So I've not included yet, but it's something to take into account for sure.